Hello, this is John Wayne. The title of the talk is Post-Selection Using Test Sets, PSUTS in AI. Since 2015, all AI papers in Nature are flawed. Here, this is the letter that I sent to Nature, editor-in-chief, and it's available from my home page. It reported 15 papers are all technically flawed using PSUTS. Outline, I talk about intro, PSUTS, why Error-BackProp needs PSUTS, developmental errors that avoid PSUTS, and conclusions. First, talk about Symbolic School. Define a set of symbols, and Brand does not use symbols, but rather numerical vectors. The meanings of symbols are in humans' mind that define the symbols, but not the meanings are not in the machines. Therefore, when these symbols are beyond what is predefined, and the system becomes very brittle. So in other words, that if the word is beyond what is predefined, and the system crashes. The Connectionist School intends to emulate how brain computes and using neurons, but the mapping defined still mapping from input space X to output space S, which is still a set of symbols. So in other words, that also brittle regardless performance of network, the predefined set of symbols cause the high brittleness. Developmental schools, on the other hand, start from a paper in Science I co-authored with 6 other courses, and it's task-nonspecific. And the first developmental program seems to be a Conception in 1992, but it does not deal with time. And like a developmental network later on, it's very concise. The total algorithm is about 2 pages long. And later on, there is a ICDO conference and IEEE AMD technical committees, and the first transaction on AMD in 2009, and the experimental system on WWN, wayward networks 1 through 9, and developmental network report lifetime error, I will talk about later, and for each set of tasks or each life, only need to train 1 network. All the comparison system need to have the same conditions. The 3 conditions that are proposed is the system restrictions. It's like what kind of framework under which the system is designed. And the second is teaching experience. It depends how the system is trained. The third is computational resource. Task-nonspecific versus task-specific framework are very different, because task-specific is easier. Human can handcraft task-specific information, but task-nonspecific framework is much more difficult and harder. The second is batch versus incremental learning modes. Here, the theory 1 is about big data flaw. All big data sets used by a machine learning method violate the sensory-motor recurrence property of the real world, because the next sensation depends on the current actions. All publicly available data sets are flawed. Another example is the hyperparameters, and the hyperplanar network determine the system architecture. Over here, A is a set of symbols, AIs, and I, you have K symbols. You have a K parameters. You, for each parameters, has 10 values, and you have 10 parameters. Then how many network you need to define? That's 10 to the 10, that's 10 billion. Another is the learning seeds. And for each system hyperparameters, you have a weight J, and J learn from 1 to N, I learn from 1 to K. Then for N equal 20, and Kn becomes 200 billion. So you search on a huge set. Machine PSUVS, post-selection using validation set, you have a training set T, validation V, and test set T prime. And validation error of network starting from AI and weight WJ is EIJ. And the post-selection using validation set try to find random weights starting seeds so that minimize the error. So EI star, J star. Machine PSUTS, instead of select the middle one from the validation set, it used the test set. It's even worse. So the error of that network, IJ, is tested on test set T prime, and T prime I star, J star becomes the best network or luckiest network from the test set. And PSUTS reports only the performance of the T prime luckiest network, but not the performance of other remaining Kn-1 trained neural networks. The correct protocol is ABCDEF here. First A, training set, validation set V, test set T prime, they are mutually disjoint. Then report validation errors of all Kn trained networks. And the PSUVS is bad because you have many networks and user did not know which one to use. You can only provide one network. Average of cross-validation of all Kn trained systems on the test sets, you report average error. Then you report the distribution of all N test errors. You want to show how the average error is reliable or not. For the best system architecture, hopefully you design a single architecture and you don't need to search. Then report the distribution of all Kn test errors of all training systems. So you can see that how the performance is sensitive to random seeds and the system hyperparameters. And if you have computations, and computation must explicitly ban all PSUTS, whether it's machine or human. Now, if we have a test on new test set, right, T double prime, then the error of the luckiest network of this luckiest network from PSUTS, the corresponding error will be very big compared to the superficial luckiest error. Now define the human PSUTS. After planning or knowing what will be in the training set T and test set T prime, a human post-select features in the networks instead of using machine to learn such features. Why Error-BackProp needs PSUTS? Theorem 2 said the error backpropagation lacks 1, energy conservation, 2, an age-dependent learning rate, and 3, computation based on low determination. And how low determination is important? All hidden neurons take random rows here because random weights determines row. Without a global plan at all because it's just random. Many rows required by the task are missing. Without competition among the hidden neurons, then you don't have missing rows to be recruited. So without competition, that automatically recruit neurons for missing rows. Each pattern of random rows largely determines the final performance because learning is greedy. For error-BackProp, it has a small luck, theorem 4, giving each input, the expected number of firing hidden neurons must be a small percentage, because each case you need to have a few neurons to be responsible for that situation. So the small percentage, otherwise updates on many inputs go to bad performance. This senior gentleman has a lot of lottery tickets. Maximum likelihood optimality versus error by propagation. Over here, you have a competition, then each top-down input from motor as a state and bottom-up from sensory input corresponding to a context. And winning, we have a win. Once the win, other neuron will not fire, the winner will fire, the link will establish through human learning, and the number here are probabilities. And without competition, and which neuron says this is the class labels, then it's like a multi-tone want to say, hey, hidden neuron, that you want to increase the value of the dark, then many neurons will require to be more, and that's error backpropagation, then you really get a mess. And hidden has 60 million parameters, and use per-selection, because if the random row pattern was wrong, then you don't really get nowhere. And actually, the luckiest network and has to be really start with the luckiest pattern of row assignment. Here is experimental result we reported earlier in CVPR workshop 2016, where this is developmental network. The first epoch of all the data is already reached the minimum result, and the error-BackProp and still going down very slowly. And this is 10 epochs. Over here, they have 100 epochs, 200, 300, 400, after 500 epochs, and the error is still larger than the DN network, because DN already optimal from the first epoch. Developmental errors. The DN only develop one network, K equal to 1 and A equal to 1. And report lifetime average and the distribution of all errors from time 0 to each current time t, and the t could be very long, and the entire life, each time you may have error, and it report the average error as well as characteristic of distribution, example, standard deviation of the errors. And why random seeds give you the same DN? Suppose you have a neuron specific age A, and I have a weight vector V, and the input X, response R, then incremental human learning lobe component analysis, LCA, is such that this update equation and is randomly initialized the weight, and when age equal to 1, and this retention rate equal to 0, and the random vector multiplied by 0 is irrelevant to the next value of V, because the learning rate is 1, and the response with the input vector will go to V right away. And so the V will only determine which neuron win, but will not affect final network that learned. Conclusions. This paper means to improve AI credibility. ImageNet contest reported misleading errors because of PSUTS. Maximum likelihood optimality of DN avoids PSUTS, since every DN is maximum likelihood optimal under the same 3 conditions. Thank you very much.